Section 15.2, Double Integrals over General Regions. If capital F, is integrable over R and D is the bounded region, then we define the double integral of lowercase f over D by the double integral of capital F over R, where capital F is our function, equal only to our function when xy is in R domain D, and 0 when it's in R not in D. So what we're basically saying is we know how to get the double integral of a function if it's over a rectangle. We don't know how to get it over a domain in general. So we take the function f and we extend it so that whenever f is outside of the domain we want to integrate over, it's inside of a rectangle. But in order for that not to mess up the value of our integral, we set that equal to 0. So we just bring f to the floor outside. So f is living above, as usual, as long as it's above the domain that we want to integrate over, but then when f exceeds that domain, it drops down to the floor. So when we integrate over a rectangle, we basically get the integral of the part that's over the domain. So it's kind of a cool little trick. Next up, we define what a type 1 and type 2 region is, because it becomes a little bit complicated to even integrate over these domains. It should make sense that when you integrate over the rectangle where f is 0 outside of the domain, all you really need to consider is the boundary parts of the domain to integrate, because if you integrate all the way from the top, then you're just putting in a bunch of 0 stuff, so you might as well just start at the domain. So then the question arises, well, how do you describe that top part, or bottom part, or left part, or right part? Well, it depends on the type of region you have. If you have a region where the top part can be described as a function of x and the bottom part can be described as a function of x, then you have a type 1 region, because it's just sandwiched between two functions of x. So that could either look like this, or it could be that on one end those functions meet each other, and then on the other end they just cut off at some x value, or it could be that the functions just end up in a point at both ends. It doesn't really make a difference either way. On the top you've got some function of x, and on the bottom you've got some other y equals function of x. So then the other possibility is that we have a type 2 region, where on the left you have a function of y, and on the right you have some other x equals function of y. And as before, that could either be completely distinct on both sides, or they could come together to a point. It doesn't really make a difference as long as there's a function of y on the left and a function of y on the right. We call it a type 2 region. So then, going back a little bit, if we have a type 1 region, then we describe the domain by saying that we have some functions of x for top and bottom. That was like this. And as far as the x values go, the x value starts at just some x value and ends at some x value. We don't really have other crazy functions on the left and right. It's basically just cut off by an x equals a line and an x equals b line. So that means that our x goes between constant values and our y goes between functions of x. So when we integrate, we have to be careful to integrate first with respect to y so that we get rid of the functions of x. And then we can have a single variable calculus integral with just constant limits like we're used to. So then if we have a type 2 region, we do the opposite. In that case, y is between two constants, because if you notice, these are basically just two y equals lines, y equals c, y equals d. But x equals curves are the functions of y. So x ranges from two functions of y. So in that case, we integrate with respect to x first, because we want to deal with all of the x equals functions of y floating around, so that when we end up with just a single variable calculus function of y, it's just between constant c and d. So this is kind of similar to when we were finding areas between curves, and we had to try to decide if we wanted to integrate with respect to x or with respect to y, and we did it based on whether it was convenient to express things as a function of x or a function of y. Sometimes it's easier to do one in terms or the other. So how about we do an example? Let's evaluate this double integral x plus 2y dA, where d is the region bounded by these parabolas y equals 2x squared and y equals 1 plus x squared. So as we're always going to want to do, we have to draw our domain D that we want to integrate over. So how about I make this the x-axis, this could be the y-axis. I need some parabolas. So how about I do 2x squared first. So let's say that this is 2x squared. And I'm supposed to make this roughly symmetrical, but it's going to be pretty hard. I need to do 1 plus x squared now, so it's floating above a little bit. And because 2x squared is multiplied by 2, it should be narrower. So 1 plus x squared should be wider. So maybe something like this. Roughly. Okay, so my bottom one is y equals 2x squared. My top one is y equals 1 plus x squared. Let's see where these guys intersect. So that would be when 2x squared is equal to 1 plus x squared. So that's when x squared is equal to 1. So that's when x is equal to plus or minus 1. Okay, so that means that if I look over here, I plug in 1, I get 2. So this is the point 1, 2 of intersection, and this is the point minus 1, 2 of intersection. And we can call this our domain D, everything over there. All right, so what type of region is this? Well, we should probably think, are these functions of x or functions of y? It looks like it's pretty easy to just say it's y equals function of x. There's one on the bottom and there's one on the top. So if I'm going to integrate, it looks like I should do that. How about I use this thing over here to indicate my direction. I'll go from bottom to top. So we'll say that this is a type 1 region. So I'm going to always draw the arrow to indicate the inner integral, the partial integral. So in this case, my inner integral goes from functions of x. It goes from y equals functions of x. So I'm integrating with respect to y first. It's type 1. So our domain is all of the points x and y such that our x is between constant values, because the other one that's not between functions is between constants, the other variable. So x goes between 1 and minus 1, and y is going between two functions of x. So y is sandwiched between 2x squared and 1 plus x squared. So when I write my double integral over d of x plus 2y dA, what I'm going to do is set that equal to the iterated integral from minus 1 to 1 outside for x, and then inside is going to be y. It goes from 2x squared to 1 plus x squared. I have x plus 2y, first respect to y, and then respect to x. And this is using Fubini's theorem, which still works because of our definition saying that this double integral over d is really a double integral over r with everything else outside 0. So just use Fubini to make it an iterated integral. And we make this equal to the integral from minus 1 to 1 of this partial integral. So that's just going to be x times y, because I'm going with respect to y, x is constant, plus y squared. And I'll have to evaluate that from y equals 2x squared to y equals 1 plus x squared dx. So that becomes the integral from minus 1 to 1 of x times 1 plus x squared plus 1 plus x squared squared minus x times 2x squared minus 2x squared squared dx. And that's just the integral from minus 1 to 1 of minus 3x to the fourth minus x to the third plus 2x squared plus x plus 1 dx, which is an easy single variable calculus integral that we can just take the antiderivative of as negative 3x to the fifth over 5 minus x to the fourth over 4 plus 2 times x cubed over 3 plus x squared over 2 plus x, all evaluated from minus 1 to 1, and it becomes 32 over 15. Remember, that's not the area inside of my type 1 region. That's the volume underneath the three-dimensional surface that's floating above this region in the xy plane. If I were to draw in 3D, then, you know, here's y, here's x, and here's z. So this little parabola kind of thing is just, you know, floating around over here somewhere. It's just, and then my surface is floating above, so, well, it's floating above just the parabola part. Everything else is 0, and then the volume in between is what we just calculated, assuming that, you know, it's floating above. Otherwise, if it's floating below, it's the negative of that. How about we now find the volume of the solid that lies under the paraboloid c equals x squared plus y squared and above the region D in the xy plane, bounded by the line y equals 2x and the parabola y equals x squared. So, as before, we need to draw it. Okay, how about I do y equals x squared? So it's something like that. I should probably name it y equals x squared. And I need, what's my other thing? Y equals 2x. So that cuts through like this. Okay, so this is my region D. And I would like to see where they intersect. Well, that's where 2x equals x squared. So x is just 2. So that's at 2, 4. And I could just put that underneath. Okay, so it looks like I've got two y equals functions of x. So I should probably just say that this is a type 1 region. I go from bottom to top first. So I'll first integrate with respect to y. So we'll call this a type 1 region. And we'll use D to describe our domain as the set of points x and y such that x is between two constant values, 0 and 2, and y is between two functions of x, x squared and 2x. So that means that our volume is our double integral over D of x squared plus y squared dA, which is by Fubini equal to the integral from 0 to 2 for x, and then x squared to 2x for y of x squared plus y squared dy dx. And that's just equal to the integral from 0 to 2 of x squared y plus y cubed over 3 evaluated from y equals x squared to y equals 2x. And that's equal to the integral from 0 to 2 of x squared 2x, plugging in for y now, plus 2x cubed over 3 minus x squared times x squared minus x squared cubed over 3. Okay, so then we can simplify a little bit more. We get the integral from 0 to 2 of minus x to the 6th over 3 minus x to the 4th plus 14x cubed over 3 dx, which is minus x to the 7th over 21 minus x to the 5th over 5 plus 7x to the 4th over 6 evaluated from 0 to 2. And it ends up just becoming 216 over 35. So you might ask now, okay, well, That's pretty cool. Let's move on. But wait, how about we take a look at this type 1 region? Notice that this is all in the first quadrant is positive. So if I want, I could write x equals the square root of y, and I could write x equals half y. And maybe I could actually do this problem differently. So let's just take a look at this again. How about I redraw the region we're integrating over. So put my parabola back, and I'll put my line back. So this is still going to be d, and I'll instead call this x equals the square root of y, and I will call this x equals half y for my line, and my point of intersection is still 2, 4. So now I've got two x equals functions of y. So I go from left to right. So for my inner integral, I'm going to be plugging in for x now. So this is now type 2. So that's pretty cool. If I was going to describe it, I could say that d is now the set of points x, y, such that y is now between constant values 0 and 4, because you just go up from 0 to 4, and x is between two functions of y, so we could say it's between half y and square root of y from left to right. So this means that we could write our volume as the double integral over d of x squared plus y squared dA. That's the function floating above. And using Fubini, we get that that's the integral from 0 to 4 for y outside, and then inside is from half y to square root y of x squared plus y squared dx dy. So that's just the integral from 0 to 4 of x cubed over 3 plus y squared x, evaluated from x equals half y up until x equals square root of y, and that's just the integral from 0 to 4 of y to the 3 over 2 over 3 plus y to the 5 over 2 minus y cubed over 24 minus y cubed over 2 dy, which becomes 2 over 15 y to the 5 over 2 plus 2/7 y to the 7 over 2 minus 13 over 96 y to the 4th, evaluated from 0 to 4, and we end up with 216 over 35 as we got before. So it doesn't matter whether we did type 1 or type 2 region, as long as we were careful to switch to functions of y or functions of x, depending on which one we were looking at, and switch the order of our integration. Notice that we couldn't just change the order of the integral. In this case, I couldn't just make this y squared and 2y and then, swap in the 0, 2, whatever it is. I had to actually redraw it, check it out, because these limits totally changed. We went from 0 to 4 now. We went from, instead of x squared, half y. So you got to be super careful. Okay, let's take a look at this double integral now. So we'll draw a region D first. Let's see, we've got parabola again, y squared. So this is an x equals parabola. When you want to think about it, at least that's the way I think about it. So how about I draw, let's see if I can do it. Something like that. And I need to cut through with the line y equals x minus 1. So that's this line, let's say, over here. And let's see. They should intersect when the two y values are equal. It's probably easier to just write them as x values though. So how about I do x equals y plus 1 for my line, and x equals half y squared minus 3 for my parabola, and then setting those equal to each other, I see they intersect at the point 1 minus 2 and the point 5, 4. Okay, so I think this is a pretty good picture. It looks like I'm going from two x equals functions of y, so I'll go from left to right. Okay, and I can now describe my region as a type 2 region. This is my first integrals from left to right, my inner one, and that means that I can say that D is equal to the set of points x, y such that y is between two constant values, minus 2 and 4. And it looks like x is between functions of y as half y squared minus 3 and y plus 1 on the right. Okay, so our double integral over D for xy becomes the iterated integral by Fubini from minus 2 to 4 for y on the outside, and then for x we go from half y squared minus 3 to y plus 1, because that's what we said x is equal to, and we integrate xy with respect to x and then with respect to y. So we get the integral from minus 2 to 4 of x squared over 2 times y. We evaluate that from x equals half y squared minus 3 to x equals y plus 1 dy, and that becomes half times the integral from minus 2 to 4 of y times y plus 1 squared minus half y squared minus 3 squared dy, and we just simplify this a little bit. We get half the integrals minus 2 to 4 of minus y to the 5th over 4 plus 4y cubed plus 2y squared minus 8y dy, and that is equal to half times minus y to the 6th over 24 plus y to the 4th plus 2y cubed over 3 minus 4y squared, evaluated from minus 2 to 4, which is just 36. So at this point you might be asking, okay, well, you kind of did that a little bit automatically. How'd you even know to do type 2 when they gave it to you as basically y functions of x? Well, let's say we were to, draw it as a type 1 region. So in that case, we would get, let's see if I can do this again now. We'll do our same parabolas as before. So something like this, let's see. And I need to cut through. All right, and we can say that this is the line y equals x minus 1 as we're given, but this thing over here is a little bit different. It's got a y squared in it. It's y squared equals 2x plus 6. So if I want to write that as y equals, then I need to take the square root. But taking the square root, I have a plus section and a minus section because part of this is below the x-axis. So that means that on the top I have y equals the positive square root of 2x plus 6, but on the bottom I have y equals minus the square root of 2x plus 6. My points of intersection are still the same as they were before at minus 1, -2 and at 5, 4. But now we would be integrating from bottom to top. So we'd have to do that for this section, where notice the bottom is y equals negative square root 2x plus 6, and the top is y equals 2x plus 6. That's over here is the bottom, and then over here is the top. But then notice that after this point of intersection over here, it switches. Now the bottom is no longer y equals negative square root 2x plus 6. Now the bottom is this line, all the way up until you get to the end at x equals 5. So that means I would have to do another integral. So I'd have to integrate with respect to y, because I've got y equals function of x. I have to do that, and then I have to integrate with respect to y again separately to accommodate for the change in the bottom. So it's pretty inconvenient to do. First, also, you have to figure out where you're starting at. Notice that now you have to plug in, see that you start at -3 for x. So to write this as a type 1 region would result in an integral. Well, it's still, I'll write it as the double integral, and then I'll use Fubini to convert it. But using Fubini results in an integral from -3 to 1. That's this first part over here, where the top is this top part of the parabola, the bottom is the bottom part of the parabola. So that means that I go from minus the square root of 2x plus 6 to plus the square root of 2x plus 6. And it's still xy, but then it's with respect to y first and then x. And I have to add another integral because I have to accommodate for the entire rest of this thing. So I start my x now at -1. This is supposed to be minus because over here this point is -1. And I go up until 5. So now my bottom, starting at -1, is x minus 1, and my top is still square root of 2x plus 6. And I've got xy dy dx. So I'd have to do both of these complicated integrals to get my answer of 36, when instead I could just write it as a type 2 region, two simpler functions, no square roots, and I only need to do one integral of Fubini. So you have to be very careful choosing which type of region. You can often write it as a different type if you really want to, but then you have to split it up. So you choose the type that makes everything most convenient. Okay, let's now find the volume of the tetrahedron bounded by these planes. So first we'll try drawing it. Okay, let's say that, I don't know, here's my x-axis, here's my z-axis, and I need a y-axis, so something like this. I'll do my plane x plus 2y plus z equals 2. Kind of cuts through like this because the plane intersects the y-axis when x and z are 0, so that's when 2y equals 2, so that's at 0, 1, 0. Maybe I'll do it a little more over so I have a little more space. There we go. So this is at 0, 1, 0. And I want to try to make this a little bit 3D. I know this is going to intersect with my other plane, x equals 2y. X equals 2y is just a plane that, you know, in the xy plane it's just a line, and then so it cuts through diagonally straight up. So that's that plane. So in order to try to draw the intersection, how about I do it like this? So they intersect. Here's this plane. The first one I drew, x plus 2y plus z equals 2. And then this will be my other plane over here. Do it like this. X plus 2y. Oh, sorry, x equals 2y. and I'm going to call this my tetrahedron T. But I figure out where they intersect in the z-axis. Well, that's when x and y are 0, so that's at 0, 0, 2. Oops. And in the xy plane, they intersect when z is 0 and x plus 2y equals 2 has to equal, well, x and y have to be equal there. So x is equal to 2 minus 2y, and x is equal to 2y. So that means that x is equal to 1, y is equal to 1/2 when z is 0, so that's this point over here. Okay. I have the region drawn in 3D. How about I figure out where it's floating over, this region on the bottom? We want to see if that's type 1 or type 2. That's our million-dollar question. So I'll draw that separately in the xy plane. Okay, so it looks like it's like a triangle in the xy plane. So it should cut out, let's see, like this. Okay, so over here is the point 1/2, 0. Because we're in the xy plane, I won't even mention z. I'll just say it's 1/2. I'll call this our triangle D. It goes up until 1 on the y-axis, so I'll put a 1 over here. And it looks like I could do this as type 1 or type 2, but I'll make it a type 1 just as default. So I'll say that this is the y equals on the bottom. So if x is 2y, that means that y is x over 2. And then over here is this part over here. So that's this guy, but z is 0 because we're in the xy plane. So I have x plus 2y equals 2. So solving for y, I get that y must be equal to 1 minus x over 2. Okay. You could have done this, like I said, as functions of y, x equals functions of y, but in this case, you know, we'll just say it's type 1 because it doesn't really make a difference either way, and, you know, by default. Okay, so we've got our type 1 region. That means that we can say that D is equal to the set of points x, y, such that x goes between two constant values of 0 and 1, and y goes between two functions of x, x over 2 and 1 minus x over 2. Oh, I almost forgot. We are integrating from bottom to top first. So I'll just draw that just to remind you. We're integrating with respect to y first, because we have y equals functions of x, and it's type 1. So that means that my volume, v, is going to be the double integral over d of 2 minus x minus 2y dA, and by Fubini, that's the integral from 0 to 1 of the integral from x over 2 to 1 minus x over 2, 2 minus x minus 2y, dy dx, first with respect to y. Okay, so this is the integral from 0 to 1 of, well, partial integration, pretty easy at this point, hopefully. We've got 2y minus xy minus y squared, just by treating x as a constant. And then we evaluate from y equals x over 2 to y equals 1 minus x over 2. And that's just the integral from 0 to 1 of 2 minus x times 1 minus x over 2 minus 1 minus x over 2 squared minus x plus x squared over 2 plus x squared over 4 dx. Okay, so even though it's kind of easy, it's not the funnest thing to do because it just gets so messy with so much stuff, but that's okay. We can still keep going. We get the integral of x squared minus 2x plus 1 after simplifying everything. And that's easy. That's just x cubed over 3 minus x squared plus x evaluated from 0 to 1, which is 1/3. So that's the volume of this guy. How about we evaluate this iterated integral from 0 to 1 for x and then x to 1 for y of sine of y squared. Actually, this seems super hard because the integral over here of sine of y squared, or as we've maybe seen before, sine of x squared dx, is impossible to compute in finite terms. It's not representable in terms of elementary functions. It is integrable. It's continuous, not really a problem, except that we can't integrate it. So we might have to take advantage of the fact that this is a double integral. So using Fubini, we could reset this thing. Well, it's an iterated integral. We can reset it to a double integral as some double integral over some region D by getting rid of these limits. And then once we have it over region D, we can maybe change the order and go from x to y instead of going from y to x. So let's try doing that. We'll use Fubini and say that this iterated integral from 0 to 1 of the integral from x to 1 of sine of y squared dy dx is equal to the double integral over d of sine of y squared dA. So now the question is, what is d? Well, as usual, we have to draw it. So here we go. And it looks like we've got y going from y equals x to y equals 1. So here's y equals x, and here's y equals 1. And put that in. And then it looks like x goes from 0 to 1, so that's good. And we can call this d. So it looks like we're integrating from two y equals functions of x. We're integrating with respect to y first, so I'm going from bottom to top. So this region is a type 1 region, which we knew because our iterated integral was first with respect to y. Okay, so that means that I could write d equal to the set of points x, y, such that x goes between 0 and 1, and y goes between x on the bottom and 1 on the top. And I would like to change the order. So I need to redraw the region as a type 2 region, so I'll draw it again. The drawing itself doesn't really change much of the actual region. All that I'm really changing is our perspective on it, because I'm just going to say that this line over here that was y equals x before is now just going to be x equals y, because I want two x equals functions. So on the left, this will be x equals 0 now. And then y integrates two constants, so it integrates from 0 to constant 1. So we cut off over here at 1. And now, since we're going from left to right, we go from x equals 0 to x equals y, we can say that this region D is now a type 2 region. So I can write, or rewrite, D equal to the points x, y, such that y is now between constants 0 and 1. And x is between functions of y. On the left, it's x equals 0. And on the right, it is x equals y. Okay, cool. So that means that my iterated integral, the original one that I was given, from 0 to 1, x to 1 of sine of y squared dy dx can be rewritten using Fubini as a double integral over d of sine of y squared dA, which can be further rewritten again after we reset it as an iterated integral from 0 to 1 now for y, and then 0 to y for x of sine of y squared dx dy. And you might say, okay, well, you didn't make any progress, you still have sine y squared. You can't integrate that, but sine of y squared is now a constant because we're doing it with respect to x. So this is not a function anymore that we have to worry about trying to find a integral for. We can just integrate it as a constant. It makes it super easy. So we're going from 0 to 1 of just x times this constant when we integrate with respect to x. So that's wonderful. We'll evaluate that from x equals 0 to x equals y. And then we get the integral, single variable calculus, from 0 to 1 of y times sine of y squared dy, because there's no contribution from x equals 0. But at this point, you're probably saying again, trying to catch me, hey, this is a mess, but it's actually way better now that we have that y over there, because now we can do a u substitution. Let u equal y squared, du is, 2y dy. So all we have to do is throw in a minus half, and we can integrate that as sine of u, which is cosine. Throw in the minus because the derivative of cosine is minus sine. We want this to be positive. So this is cosine of y squared. You could try testing that. Take the derivative. The 2y hops out, cancels with the half, and then you just have the y, and then the minus disappears when you take derivative of cosine because you get minus minus sine. Okay, and we evaluate that from 0 to 1. So that's just 1/2 1 minus the cosine of 1. Pretty cool. So that integral would have been super hard if it wasn't a double integral that we converted. You have to be a little bit careful with this stuff because notice they didn't tell us find the volume or do it as a double integral. They didn't give you your domain D. You had to use your limits, work backwards to Fubini to construct D, and then rewrite the functions of x as functions of y. So instead of going from bottom to top, we went from left to right. Notice that we couldn't just swap these guys because replacing this with a y would make it go from y to 1, which wasn't what ended up happening. We went from 0 to y. So you have to be very careful changing your limits. You have to redraw it in order to see where it's going to go, unless you have very good visual perception in your head. Then I guess you don't have to draw it, but I'm not that good. Let's now talk about some properties of double integrals, which are very analogous to the properties of single integrals. The double integral of a sum, it turns out, is the sum of double integrals, as we would expect, and the double integral of a constant times an integral, the constant can just be pulled out, as we would expect. So that means that our double integral is has linearity. Also, if we have one function bigger than another function, so one z value on top of another, then that means that there's more volume underneath this guy than this guy, so it makes sense that the double integral of f would be greater than or equal to the double integral of g. Next up, we briefly discussed this possibility when we were looking at a type 1 region that had to be split. If you have a complicated region that doesn't immediately look like it's type 1 or a type 2, then you can just cut it up. And you cut up as many pieces as you want until you have pieces which are just consistently functions of x or functions of y. So in this case now you've got type 1 region over here because you've got 2y equals functions of x. So you go from bottom to top, but then over here you would go from left to right because this looks like an x equals function of y on the right. So you can just cut up your integral into two double integrals and then integrate away happily. Next up, if you take the double integral of 1, then you just get the area, which makes sense because taking the single integral of 1 gave you the length of the interval you were integrating over, so it should make sense that taking the double integral should give you the area. You can imagine that you're taking the double integral over just some flat thing floating. This is like usually surfaces, they wave a little bit, whatever, so they have some volume underneath, which is interesting. But if you take the double integral over a flat thing that's exactly 1 up in the air, then the volume of this thing is just the area times 1. So then it's just the area. If we have our function bounded by 2 constants, so it's less than or equal to capital M and greater than or equal to lowercase m, then that means that our integral is also bounded by those constants. You just have to throw in the area. So it makes a little bit of sense why that's true, because we had the same estimate for single variable calculus where we had bounded by m times b minus a and m times b minus a, which was the length of the interval. But again, we're not integrating over an interval, we're integrating over domains, so we don't talk about lengths, we talk about areas. So how about we apply that really quick, and we use it to estimate this integral over here without actually having to calculate it. So d is the disk with center of the origin, radius 2. And we're trying to estimate this, so we need to bound this function. So in order to bound e to the sine x cosine y, how about we just look at that trig part first, because we know that sine is bounded by -1 and 1, which is nice. And cosine is also. So that means that if I want to look at the product, multiplying, the biggest it could possibly be is 1, the smallest it could possibly be is -1. So the product is also bounded by -1 and 1. So that means that I could just raise all sides to e. So that gives me that e to the -1 must be less than or equal to e to the sine x cosine x, which would be less than or equal to e to the 1, which is just e. So how about I set m, little m, equal to e to the -1, which I could just rewrite as 1 over e. And I'll set big M equal to e. So I also need the area, so the area of our domain, in this case is the area of the disk with center of the origin, radius 2. Center doesn't matter, but the radius tells me that the area is pi r squared. So that's pi times 2 squared. So that's 4 pi, so that means that I could say that it's 4 pi times little m, so that's 4 pi times 1 over e, which is 4 pi over e. That'll be less than or equal to our double integral, e to the sine x cosine y dA, which is in turn less than or equal to area of d times capital M, so that's 4 pi times e.